All right, this is CS50, and this is week 5 already, wherein we will focus today on data structures, which is a topic we've touched on a little bit in simple form, but today we'll dive all the more deeply. And for better or for worse, this is our last week on C. Next week, of course, we transition to Python, which is a so-called higher level programming language, which is really, frankly, just going to make our lives a lot easier. We're going to be able to solve a lot of the same problems, but so much more quickly as humans, but not necessarily as we'll see as fast when we run the code as the computer might have if we were still using a lower level language like C. So indeed, thematic over this week and next is going to be the theme that we've seen before of trade-offs. But before we get there, why don't we focus on a couple of data structures that you might encounter in the real world, namely stacks and queues. Let's learn some facts about both of these. If we could dim the lights dramatically.
Once upon a time, there was a guy named Jack. When it came to making friends, Jack did not have the knack. So Jack went to talk to the most popular guy he knew. He went up to Lou and asked, "What do I do?" Lou saw that his friend was really distressed. "Well," Lou began, "just look how you're dressed. Don't you have any clothes with a different look?" "Yes," said Jack, "I sure do. Come to my house and I'll show them to you." So they went off to Jack's, and Jack showed Lou the box, where he kept all his shirts and his pants and his socks. Lou said, "I see you have all your clothes in a pile. Why don't you wear some others once in a while?" Jack said, "Well, when I remove clothes and socks, I wash them and put them away in the box. Then comes the next morning, and up I hop. I go to the box and get my clothes off the top." Lou quickly realized the problem with Jack. He kept clothes, CDs, and books in a stack. When he reached for something to read or to wear, he chose the top book or underwear. Then when he was done, he would put it right back. Back it would go on top of the stack. "I know the solution," said a triumphant Lou. "You need to learn to start using a queue." Lou took Jack's clothes and hung them in the closet, and when he had emptied the box, he just tossed it. Then he said, "Now Jack, at the end of the day, put your clothes on the left when you put them away. Then tomorrow morning when you see the sun shine, get your clothes from the right, from the end of the line." "Don't you see," said Lou, "it will be so nice. You'll wear everything once before you wear something twice." And with everything in queues in his closet and shelf, Jack started to feel quite sure of himself, all thanks to Lou and his wonderful queue.
All right, our thanks to Professor Shannon Duvall at Elon University, who kindly put together that animation. And it's meant to paint a picture of a couple of things that we've all encountered in the real world. But more technically, what we just saw were what are known as abstract data types, whereby they're data structures in some sense, but it's really about the design thereof, what characteristics or features or functionality these structures offer, irrespective of how they are implemented in terms of lower level implementation details, which is to say you can implement, as we'll see, queues and stacks in any number of ways, which are going to have real world implications for how you can actually use them and what kinds of problems you can solve with them. So let's consider, for instance, queues in the first place. So a queue is something you sort of experience all the time. Anytime you go to a store, go to some event for which you have to line up in a so-called queue, you'd ideally like there to be some fairness property about that queue, such that if you got in line first, you get into the store first, you get to check out first, or some other such goal. Meanwhile, the person who got there last actually is at the end of the line and stays at the end of the line and therefore gets served or enters in at the end. So queues have what computer scientists would say is a FIFO property, first in, first out. That is, if you're the first person in line, you're the first person to get out of line. And for many problems, that is a good solution, certainly if you're concerned with fairness. But more technically, a queue has what we'll call two operations. NQ, which is a fancy way of saying getting in line, and DQ, a fancy way of saying getting out of the line from the front of it. But those two operations, if you think about it in code, could it be implemented with different actual details? And by that I mean this. Here is one way that we could go about implementing in C code a queue for a bunch of people or persons who want to line up for something. So for instance, we'll decree that this queue can hold no more than 50 people, like that's the physical capacity. And then we define a structure, which we've done a couple of times in the past, whereby this structure has not only an array of persons that we'll call people, and that will be as big as is the capacity. So this is an array of size 50 for 50 such persons. And then we're going to propose that we also keep track in this implementation of a queue of the current size of the queue. So we're going to make a distinction between the capacity, like how many total people can be there, and the size, like actually how many people are in line at that moment in time, so that you know which of the spots in the array are effectively empty. And we're going to call that whole structure a queue. Now, the catch with this particular implementation in code of a queue is what? There is inherent in it a limitation, something you just kind of have to deal with. And I see you nodding. What's your instinct for this?
For example, like you have like 50 students.
OK, well, I think you hit the nail on the head in that it's only for 50 students or 50 people, which means if a 51st person wants to get into line, you literally have no means of remembering them in this data structure. So how do you solve that? Well, we could just recompile our code after changing the 50 to like 51 or maybe 500 or 5,000. But there's this trade-off, because you could still be undershooting the total number of people trying to get into maybe a big concert in the case of an extreme. But at the same time, if you over-allocate memory using 5,000 locations in memory, what if only a few people show up? Now you're just wasting memory. And certainly at the end of the day, you only have a finite amount of memory in the computer. So you kind of have to decide a priori, like before compiling your code, how big is this structure going to be? How much space are you going to waste? And in the end, it's all sort of stupid. It would be ideal if instead we could just grow the queue as needed and shrink it, essentially asking the operating system, as we started doing last week, for more memory, and then giving it back if we don't actually need that memory, which is to say, can't really do an array in this static sense. And by static, I mean we're literally deciding in advance at compilation time how big this thing is going to be. As an aside, this is also a bit annoying for implementing a queue, because you have to somehow keep track of who is at the head of the queue, the front of the queue, because as you start plucking people off, you need to remember who's the next person effectively. But there are ways in code that we could solve this. So let's consider an alternative to a queue, which gives us very different properties, namely a stack. And we saw that in the animation, whereby Jack used a stack to put his clothes into a box, so that every time he got dressed, he sort of took the sweater from the top, from the top, from the top, and might never wear anything other than black as a result, if he does a wash before he actually reaches the blue and the red sweater there. So a stack, as we've just seen, has a LIFO property to it, last in, first out. So if I do a load of laundry and I plop some more sweaters on this stack, well, I'm presumably going to use the last sweater that went in first, as opposed to trying to create a mess and, like, pull the bottommost sweater out, which is just going to be a little more effort than it would be otherwise from just taking it from the top. So sometimes last in, first out doesn't give you maybe this fairness property you might want for other problems, but it does give you an efficiency, a convenience, certainly. So maybe that might be compelling. And stacks are actually everywhere too. If you've checked your Gmail recently, odds are you've opened up gmail.com or outlook.com and you've looked at your inbox, and where does the new mail by default end up? At the top, at the top, at the top. And I dare say all of us are guilty of sort of neglecting emails that fall below the break or onto the next page, and sort of focusing only on the last in, and therefore replying to it first out, which isn't great maybe for the senders of those emails, but it's just how those user interfaces are implemented quite often, unless you override those default settings. So how might we implement a stack? Well, we need to implement, more technically, two fundamental operations. The analogs of enqueue and dequeue in the world of stacks are called push, which means push something onto the top of the stack, and pop, which means remove something from the top of the stack also. And the team in the cafeterias and dining halls on campus do this all day long. Any of the cafeterias or dining halls that have stacks of trays, of course, you put the first tray at the bottom, and then the next tray, and the next tray, and the next tray. And which tray do all of you pick up? Well, presumably the one on the very top, because it's even harder to grab the bottommost tray than it would be for something like a sweater. As a result, there's maybe undesirable properties, like maybe no one ever gets to the nasty tray at the very bottom of the stack, because we're constantly replenishing the top ones. But thanks to gravity, like that just happens to be the most appropriate data structure in the real world for distributing things like trays in a cafeteria. So how might we implement that idea in code? Well, funny enough, we can pretty much use the exact same structure. We could just rename queue to stack, because at the end of the day, we need to keep track of some number of people. And maybe people is a weird sort of analog here, but we kept everything else the same, so why not that? But the size is also something we still need to remember. And it turns out it's a little easier to implement a stack in this way, because you could always remove it from the end of the array, and the first thing that went into the stack, the first in, can always stay at location 0, for instance. But ultimately, we could implement it in this way, but we have the same darn limitation. You can still only put 50 sweaters, 50 trays, 50 people into that stack data structure. So this is just one implementation approach. But that doesn't mean that's necessarily a limitation of stacks and queues. They're abstract in the sense that we could do better. We could maybe start to manage our own memory, move away from statically defining the total size of this array, and just start allocating and deallocating. That is, growing and shrinking the data structure instead, which is to say we can make these abstract data types much less abstract with actual implementations. Let's consider a data structure that we saw, an abstract data type that we saw early on that we didn't necessarily give this name. A dictionary is yet another abstract data type that's sort of everywhere in the world, literally in the world of dictionaries containing words and their definitions. And you can think of a dictionary really in the abstract, if you were to draw this on the chalkboard, as really just a two-column table, whereby on the left is the word and on the right is the definition. If it's a physical book, it's essentially the same thing with lots of columns of words on the left, often bold-faced, and then the definitions right next to them. You can also see this in the context of like a phone book, which is where we began the course in week 0, where it's essentially a dictionary of names and numbers instead of words and definitions. And a computer scientist would generalize the notion of a dictionary further and just call the thing on the left a key and the thing on the right a value. And these things are omnipresent in computing. And you're going to start to see them all the more today and next week and beyond, in that if you just want to associate some piece of data with another piece of data, a so-called key value pair, a dictionary is going to be your go-to data type. But even these two we can implement in different ways for reasons that we've already seen, like maybe there's only a finite size to this dictionary. If we're using an array, maybe we can do better than that. And maybe a dictionary, if implemented one way, is going to be fast. Maybe if implemented another way, is going to be slow. So we'll consider these other design possibilities today, too, in the context of phone books and other data structures as well. After all, if you have an iPhone or an Android phone and Apple or Google only decided that you can have 50 friends because they implemented the Contacts app in an array, I mean, that would be an annoying limitation. So presumably, they've done things a little more dynamically, as we'll do today. So let's focus on the first of the data structures we saw back in week 2. That is an array, which recall was just a chunk of memory where you can store values in it back to back to back. And that was the fundamental definition. The values are back to back to back or contiguous in memory. And as we've seen, we generally have to decide in advance the size of an array. So for instance, if we want to store 3 values, like 1, 2, and 3, it might look pictorially like this. Or in code, let's go ahead and implement this same idea and take a moment to whip up our very first program here. And we'll call it, say, list.c. And in this program, let's just do something demonstrative of how you could use arrays to store 3 things in memory. It's quite simply the numbers 1, 2, 3, but you can imagine it being 3 people's names, 3 sweaters, 3 people, or any other piece of data as well. So I'm going to go ahead and at the top of list.c include standard.io.h. I'm going to then do int main void, so no command line arguments. Then I'm going to go ahead and give myself an array of integers of size 3 called list. And that's how we've done that from week 2 onward. Then just for the sake of discussion, I'm going to hard code some representative values. So the first value will be at location 0, because arrays are 0 indexed. Then I'm going to do the second value, which will be 2. And then the third value, which will be at location 2, but the value will be 3. Now, just to prove that we've stored this correctly in memory, let's just do a quick for loop. For int I equals 0, I is less than 3, I plus plus. And then inside of this for loop, I'm just going to do a quick printf of %i\n, printing out the value of list at location I. So it's not a useful program per se, but it gives us an array to play with. It prints out what's in it. So hopefully we will see 1, 2, and 3 on the screen. So let me make this list program. /list, enter, and voila, we're on our way going. All right, but what if now we actually want to change that design and be like, oh, shoot, I now have a 4th number that I want to store, or just bought a 4th sweater, or a 4th person wants to get in line, or I want to add a 4th friend to my contacts. Whatever the scenario might be, it stands to reason that ideally you would plop that 4th value right here in memory so that everything remains contiguous. You're still using an array. Your code doesn't really have to change except for the length. For all intents and purposes, it's the same implementation using just a bit more memory. But recall that when you declare an array of a fixed size, you only are getting promised that chunk of memory, not necessarily more memory to the right, to the left, above, or below conceptually, because recall, in the context of your whole computer, you've got this canvas of memory, all of which represent here bytes, and there could be a whole bunch of actual values or garbage values in memory. So in a more complicated program, that 1, 2, 3, sure, might end up here. But if I also had created a string in this program, HELLO, comma, world, might have also ended up right next to it in memory, which means I can't just plop the 4 here, because then if I'm still using that string elsewhere in my program, now it's going to say hello world instead of hello world, because you're just claiming the H, that byte, as your own, which does not, in fact, belong to your array. Of course, it looks like there's plenty of other memory I could use here, because these garbage values represented by Oscar are not being used. They've been used in the past, but we treat garbage values as memory we could reuse, certainly. So wouldn't it be nice to maybe just plop the 1, 2, 3, and 4 in this chunk of memory over here? And I can totally do that. But of course, if I want to do that, I got to copy the first 3 values over and then put the 4th one there, and then presumably give back to the operating system the memory I no longer need. So that, in fact, when using arrays, is a perfectly valid solution. And I think we can go ahead and do this in our same program. So let me go back to VS Code here. And instead of statically allocating memory for this array, and by static I mean literally hard coding the number 3 here in a way that is permanent, effectively, let me go ahead and do this instead. At the top of my code, let me delete the static allocation of that array before, and now let me leverage my understanding, if still preliminary, of pointers and memory management from this past week 4 to just dynamically allocate a guess at how much memory I need initially. So I'm going to go ahead and use malloc and allocate space for 3 integers. But integers take up a few bytes, and it usually is 4. But just for good measure, I'm going to say times whatever the size of an int is the total number of bytes I want. So presumably it's going to be 3 times 4 equals 12. But I'm generalizing it. But then recall that malloc returns the address of that chunk of memory, the address of the first byte. So if I want to create an array effectively called list, I can't just do int list like this yet. But what I could say is that, all right, now my list variable is actually going to be the address of an integer, and set malloc's return value equal to that. So in code here, what I've done is I'm asking on the right-hand side, the operating system, please give me 12 contiguous bytes in memory. All of those bytes, of course, can be numerically addressed, like 0x123, 124, 125. We've had that story before. Malloc, by definition, returns the address of the first such byte. And it's on me to remember that I allocated 12, if need be. So I'm just storing the address of that first byte in a pointer called list. But recall from last week, there's this functional equivalence we saw between treating a pointer as an array and sometimes even treating an array like a pointer. The C language sort of lets us do this conversion, if you will. So what I could do here now is quite the same syntax as before. I could say list bracket 0 gets 1, list bracket 1 gets 2, list bracket 2 gets 3. And even though I have this fancy new line inspired by week 4, the syntax thereafter can be exactly the same. Why? Well, recall that these 3 lines here, using square bracket notation, is just syntactic sugar for the stuff we learned last week. Specifically, I could, instead of doing list bracket 0, I could much more arcanely say, go to that address in list and put the number 1 there, please. I can say, go to the address list plus 1 and put the value 2 there. I could then say, finally, go to the address at list plus 2 and put the number 3 there. But this looks ridiculous. And even sort of an experienced programmer might not be inclined to do this if, with using fewer keystrokes and more readable code, they could just do instead what I did the first time around, which is functionally the same, and just treat that chunk of memory as though it's an array. And the computer will essentially do the requisite pointer arithmetic to figure out where to put 1, 2, and 3. So even though this is still kind of fresh, hot off the press from last week, it's exactly the same as we tinkered with last week. So suppose now that some time passes and I realize, for the sake of the story, that, oh shoot, I need more than 3 integers. I need space for 4 so as to achieve this picture in memory. Well, I could, of course, just like delete all that code, change the 3 to a 4, redo the whole thing, recompile the code, rerun it. But let me propose that we write our code in a way that allows us to change our mind while the program is running how much memory we actually need. In case in point, if you meet someone new, you want to add them to your phone, well, you obviously don't want to have to wait for Apple to recompile the Contacts app, reboot your phone just to add one more person. You want the program just to ask the operating system for more memory for that new person. So in this case, let's just pretend that some time passes, and now I want to go ahead and actually change my mind and instead allocate space for 4 integers instead. Well, I could do something like this. I could just say literally list equals malloc of 4 times size of int, semicolon. I don't need to redeclare list on line 13 because it already exists from line 5. But this is bad, because what have I done wrong here in line 13? I've made a poor decision. Yeah, in front. Yeah, I'm wasting all of the memory I had from line 5 because I'm essentially forgetting where it is. If the list pointer is literally a pointer, like a foam finger pointing somewhere in memory, what I'm really doing is saying point it over here now. But I've completely lost track of those other 3 integers in memory. And that's what we described last week as a memory leak, which you could find with Valgrind. And if you didn't find it or fix it in code, eventually the computer and the program would slow down over time. So this is probably bad. It's not good to just unilaterally change your mind and say, no, 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 forget about that memory. Give me a new chunk of memory, especially if you want to copy the old memory into the new, just like I did a bit ago when trying to get the 1, 2, 3 into the bigger chunk of memory that can fit 1, 2, 3, 4. So how might I do this? Well, a temporary variable is kind of our go-to solution anytime we need to remember something in addition to something we already have in mind. So let me just give myself a temporary variable called TMP, by convention for short, and set the return value of this malloc call to that. And then what I could do is something like this. Much like my print statement earlier, I could do another for loop and say for int I equals 0, I is less than 3, I++. And then in this for loop, I could say treat that new chunk of memory as an array, like we can, set the ith location equal to the ith location in list. So these lines here copy old list into new list. It copies those first 3 values. And then what I bet I could do at the bottom here is then, just manually, I can say go to the 4th location, which when you 0 index is technically bracket 3, and set that equal to the number 4. So these lines here copy the 1, the 2, and the 3 using a loop. And then line 20 here at the moment just adds the 4th value. And again, this is a stupid sort of way to write code in that if you want to put the 4 there, you should have just done it earlier. I'm just pretending that some time has indeed passed in the program, and I've changed my mind along the way, and I want to let the user add some value to memory. OK, but before we proceed further, I dare say that there are some other mistakes we should clean up. One of the lessons I preached last week was that anytime you use malloc, what should you do or check for? You should always what? You should always free. So here I'm clearly not freeing any memory, so I should definitely do that. And there was one other rule of thumb with memory. What should you always do when using malloc? Yeah? Check to see if null came back, which just means something is wrong, like it's out of memory or something else went wrong. And if you don't do that, your program may very well crash with one of those segmentation faults that we saw briefly in the past. So it makes the code a lot more bloated, but it is good practice. So let's just check if the list pointer I get back contains null. There's no point continuing on. Let's just go ahead and immediately return 1. Because something has indeed gone wrong. And then down here, under malloc again, let's do the same. If the temporary pointer also contains null, now let's go ahead and similarly return 1 or any other non-zero value. But here's the subtlety, and let me combine your 2 ideas. If I immediately return 1 on line 20 after the second malloc call fails, what should I still go back and do first? Yeah, you want to elaborate on your first instinct? Yeah, I want to still free the first chunk of memory, because if we execute line 5 and all is well, which means that line 6, 7, 8, and 9 don't apply, like it's not in fact null, we got back a legitimate value, that means we have a chunk of memory given to us for 3 integers, which means it still exists down here at line 19 and 20. So if I'm ready now to abort this program and return 1 to signify error, I first want to free that original list and say to the operating system, here's your memory back. Now, as an aside, strictly speaking, this is not necessary because the moment the program itself quits, the computer is just going to give back the memory to the operating system. So when programs quit, the memory leaks sort of go away, but your code is still buggy. And generally, we're running software that doesn't run for a split second, but for minutes, hours, days, continually, in which case it's best practice to squash these memory-related bugs now, check for null, free any memory so that you never indeed encounter these kinds of leaks. All right, so let's forge ahead a little bit more. And let me propose that after we have done the copy, we now want to similarly free the original list. However, what I think we're going to want to do first is, after freeing the original list, is remember that the new list is effectively that which we allocated the second time around. So even though this program's getting a little long, notice that what I've just done is I've said, OK, store in the list variable the address of this new chunk of memory, so that list now with a foam finger is effectively pointing here instead of up here. But before that, I made sure to free what my finger was pointing at originally, the list pointer. All right, lastly, let's just scroll down to the bottom of the code here. I can manually change the 3 to a 4 just to demonstrate that I've stored all 4 values in here. And then at the very end of the program, I think I have to free the list again, because now list is pointing, a la the foam finger, to the bigger chunk of memory, the 1, 2, 3, 4. And then I can go ahead and return 0 at the very end, because all is hopefully well at this point. Let me go ahead and open my terminal window again and make this version of list. I made a lot of mistakes here, it seems. Let's scroll up to the very first. Call to undeclared library function malloc, ... What have I apparently done wrong or forgotten? What have I done wrong? Yeah, in back? Yep. Yeah, so in standard lib.h is where malloc is actually declared. So let's just add that quickly. Let's go ahead and include standard lib.h in addition to standard io.h. Let me clear my terminal window, rerun make list. Enter. Now we're good. /list, and phew, we see 1, 2, 3, 4. OK, so at this point in the story, all we've done is write a dopey little program that allocates memory for 3 integers, 1, 2, and 3, then changes our mind and allocates more memory for 4 integers, freeing the original chunk of memory after copying the first 3 integers into the new memory and adding that 4th value. But this is kind of a lot of hoops to jump through. And let me propose one refinement here. So if back in VS Code, we go back into list.c here, it turns out that at least this loop isn't strictly necessary, not to mention the fact that we already have another loop for just printing the list. If I want to more cleverly reallocate memory, it turns out that there's another function that we didn't talk about last week, but is in standard lib.h2 called realloc, which, as the name kind of suggests, it reallocates memory, but a little smarter in that it will try to grow your existing chunk of memory if it can, which is going to be super efficient, because then you can just plop the 4 at the very end. Or if there just isn't room there, because maybe someone else put hello world right there in memory elsewhere in your program, it's going to do all of the copying for you. So what you get back ultimately is a pointer to the new chunk of memory containing all of the original data as well. However, we're still going to have to check for null. We're still going to want to free the original list if something goes wrong and then return 1. We're still going to want to add the 4th value, because realloc has no idea what more we want to put in the list. But I can, in fact, delete my other for loop, whose purpose in life was just to copy all of those integers from old into new. All right, that was a lot. Let me pause for any questions.
How does realloc know that it should reallocate the memory in list? Should you tell, like, if you have a lot of mallocs before, how does it know which one specifically it needs to reallocate?
Very good question. That's because I wrote a bug that we didn't trip over because I didn't compile this version of the code. So the question is, how does realloc know what to realloc? Well, according to the documentation, which I forgot to read, you need to tell realloc what the address is of the chunk of memory that you do want to realloc. So the first argument to realloc, which I did admittedly forget until a moment ago, is to put the address of the chunk of memory that you already malloced earlier, so that it knows to go there, see if there's indeed some garbage values it can reclaim at the end of that chunk of memory, or if it has to wholesale move things elsewhere in memory to give you 4 times the size of the int this time instead of just 3. But still, things can go wrong. Like, you still want to check for this null value, because realloc might not be able to give you enough memory, or your memory could just be so fragmented that even though you want 4 bytes, maybe there's 3 bytes over here, 2 bytes over here, 1 byte over here. If there aren't 4 contiguous bytes, realloc 2 could fail, and it will return null to signify as much. Other questions on any of this? Why do we still need the temp variable? For the same reasons as before, because if we just say list equals realloc and something does go wrong, realloc by definition will return null, but not touch the original memory, in which case we have now lost track of where that original chunk of memory is, so we can never go back to it to print it, to change it, to free it. So we have to use this temporary variable here. Good question. Other questions? Yeah? So realloc will do two potential things for you. So if the computer's memory looks like this, you're sort of out of luck because realloc can't give you this byte. However, if it finds like 4 bytes down here, for instance, realloc will not only allocate those 4 bytes for you, it will then copy the data for you over to it, which is wonderful because it just means we don't need an extra for loop all the time we do this. Yeah, in front. How does it know how much data to? Because how does realloc know how much data to copy? Because the operating system, and you can think of it as the standard library, stdlib.h, keeps track of what memory has been allocated for you in the past. So when you pass in that same address, it knows it has essentially a lookup table, a dictionary, if you will, that tells it what memory has been allocated already. So you don't have to worry about that. Yeah, in front. Among the goals here was to demonstrate that there are a bunch of ways in which we can implement these data types. But let's talk more concretely about what we'll call data structures, which are concrete definitions of how you use the computer's memory to lay stuff out in memory. And using data structures, you can implement stacks and queues and dictionaries and all of these other things. So we're going to put into your toolkit today a whole bunch of canonical data structures that, like every computer scientist does and should know, that you won't necessarily implement all of the time yourself. But when you use some feature of Python or Java or C++ or some other language, you are choosing among typically implementations of these data structures that someone else has written the code for, so that you can just benefit from the functionality and the features thereof, like that FIFO property we talked about, or LIFO, without having to get into the weeds too much yourself. So when it comes to data structures, let's consider that we have at our disposal now a few new pieces of syntax in C, and we're going to add just one more today. We saw last week that we have the struct keyword, and we've seen that for a few weeks now. Whenever we want to invent our own data structure, we can use literally struct. We saw in the past that you can use the dot operator to actually go inside of a structure to get at a person's name or their number. And we saw last week the star operator for dereferencing a pointer, dereferencing an address to actually go somewhere, like inside of a structure. Wonderfully, today, we're going to see that you can actually, in some cases, combine the dot and the asterisk into a single operator with 2 characters that literally looks like an arrow. And that will help reflect the yellow and black drawings that we've done over the past couple of weeks, where we have an arrow on the screen pointing somewhere. This literal arrow in code is going to line up with that same concept. So let's introduce the first of our alternatives to arrays. An array, again, is a contiguous chunk of memory where the values are back to back to back. Among the upsides, so fast, because like all of the data is right there. We've seen since week 0, you can do binary search and just jump around randomly by just doing simple arithmetic to go to the middle of the middle, by just dividing by 2 a couple of times and rounding as needed. But the problem with arrays, to be clear, is that they are statically allocated to be a specific size, maybe 3, maybe 4, but it is a finite value, which is problematic because look at all of the code we had to write just to resize these things again and again. Well, what if we sort of try to preempt that kind of pain and try to just build up a list by linking it together no matter where the values actually are in memory, and move away from this constraint that everything has to be contiguous. After all, as I said a moment ago, if the computer has plenty of memory here, 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 that collectively is more than enough memory, but none of those individual chunks is quite as big as you need for an array, well, heck, let's at least try to leverage all of the available memory and stitch together the data structure, as opposed to really holding firm this constraint that the array be back to back to back and contiguous. So a linked list is something you can now build using that syntax from last week and a bit more today in your same canvas of memory, so that for the sake of discussion, suppose that we want to store first in our list the number 1. Well, we all know already that it might very well exist at an address like 0x123 for the sake of discussion, but it's somewhere there. Suppose that you want to store a second value in memory, but you didn't think about it initially, and so you weren't smart enough to put it like right next to the 1 and then the next value next to that. But you know somehow from malloc or similar functions that you could put the number 2 over here at address 0x456 for the sake of discussion. And similarly, there's room for the number 3 over here at, say, address 0x789. So already we have a list of values in memory, but because they're not contiguous, you can't just do some trivial plus trick to go from one to the other, because they're differing numbers of bytes apart. They're not just back to back 1 byte. So what if we try to solve that problem in the following way? Instead of just using 1 byte for each of these values, let me waste a little bit of memory, or spend a little bit of memory, and have some metadata associated with our data. So data is are values you care about. Metadata is data that helps you maintain the data you care about. So let me propose that we use 2 chunks of memory for every value, such that the top of each of those chunks represents the actual value we care about, 1, 2, and 3 respectively. And you can perhaps see where this is going. The second chunk of memory that I've allocated to each of these values could perhaps be a pointer to the next one, a pointer to the next one. And if this is the end, we can put our old friend 0x0, aka null, and just treat that as the end of the list implicitly. So even though these things could be anywhere in memory, by just storing with each value the address of the next value in memory, creating effectively a treasure map or breadcrumbs, however you want to think of it metaphorically, we can get from one node to the other. And indeed, that's going to be a term of art we start using. A node is just a generic structure that contains data and metadata, usually, like the number you care about and a pointer to the next such node. These are not to scale as an aside. This is typically 4 bytes. A pointer, as we've discussed, is technically 8 bytes, but it just looks prettier to draw them as simple squares on the screen. So what does this really mean? Well, who really cares about 0x123, 4, 5, 6, 7, 8, 9? We can really think of this actually as being more of a picture with arrows. But to keep track of this list of 3 values, I do propose that we're going to need 1 additional value over here. And it's deliberately just a single square, because to keep track of this list of 3 values, I'm going to use just 1 variable called, say, list, and store in that variable a pointer, as we defined it last week, the address of the first node. Why? Because the first node can then get me to the second. The second node can then get me to the third, and so forth. So what's the upside now? If I want a 4th value somewhere on the screen, I could put it here, 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 wherever there's enough room, and just make sure that I update the arrow to point to that next chunk. Update the arrow to point to the next chunk. There's no copying of data. 1, 2, and 3 can stay there now forever until the program quits, and we do actually free it. But we can just keep adding, or growing this data structure in memory. So that is what the world knows as a linked list. In Python, to which you were essentially alluding, a list in Python is indeed a linked list. Other languages call these vectors, but they are essentially arrays that can be grown and shrunken automatically, effectively, without you having to worry quite as much about it. So how does the code for implementing something like this work? Well, let me propose that we have this familiar friend of a person, which we claimed in past weeks has a name and a number associated with them. We know from last week that strings are not technically a thing in C as a keyword, so that's technically just char star, name and number, but same idea otherwise. And this is what we defined in the past as a person. So this is a structure we've seen before. I now need to implement the code equivalent of these rectangles, each of which has an integer and then a pointer to the next such value. So let me propose that we delete what's inside this structure, change the name from person to node, which again is the generic term for a container of values. And let me propose that inside of this new node structure, we put literally an int for the number we care about. There's going to be my 1, 2, 3, or 4. And then, and this is a little bit new, let's include in this structure a pointer to the next such node. It's a pointer in the sense that it's an arrow. It's the address of the next node. So that's why we say node star. I could call it anything I want, but semantically calling it next makes perfect sense because it's the next such node. But this isn't quite right. For annoying technical reasons, I need to do one other thing here. I need to technically, and we've not done this before, put the name, give a temporary name to this structure, if you will. So literally say struct node here, even though I've already said node here. Why? Because I technically need to change this line to say struct node star. Long story short, why is this necessary? Well, recall in the past, C and the compiler reads your code top to bottom, left to right. Well, if we, in a previous version of this code, we use the word node here, but the compiler never sees the word node until down here, like it's just not going to compile because the word literally doesn't exist. We saw this with functions in the past. So the solution to that was to put the prototype higher up in the file, and then it would compile OK. You can think of this as somewhat analogous, whereby if I give this structure a name on this first line, even if it's redundant to this one, then I can say struct node inside of these curly braces because the compiler has already seen the word node there. So just, you have to do it this way. So now that we have this in code, we can kind of start playing around with actually storing these things in memory. So let me propose that we go ahead and do this by transitioning back to VS Code here. And let's, instead of using our array-based implementation, let's implement the first of our linked lists. And I'm going to be a bit extreme and delete pretty much everything inside of main. I am, for convenience, now going to include the CS50 library, not so much for the char star thing, but because, as we discussed last week, it's still useful for getting ints and getting strings and other things, which, instead, unless you use scanf, are much harder and more annoying to get in C. So let's go ahead and do this. Outside of main, let's go ahead and invent this node called struct node here. Then inside of my curly braces, we'll give every such node a number and every such node a pointer to the next such node. And we'll call this whole thing node by convention. Then inside of main, let's go ahead and do this one step at a time. Let me propose that to create a linked list initially, it's empty. So how do I represent an empty linked list? Well, I could call the variable list and set it equal to null. But what is the data type for a linked list? Well, per the picture that we had up earlier, insofar as all we need is a single pointer at far left here to represent the address of the first node in the list, I dare say all we need to say is that our list is of type node star. That is to say, what is the linked list? Well, it's by definition the address of the first node in the list. So that's the first subtlety here. So that gives me a picture with no other nodes. It just gives me a single pointer initialized to null. Now let's go ahead and, for parity with the previous example, just do something 3 times. So in this for loop, structured exactly as before, let's go ahead and allocate a new node, ask the user for a number to put inside of it, and then start stitching things together so as to achieve a picture in memory quite like this. So how am I going to do this? Well, first I need to allocate a new node. How do I do that? Well, I can use our new friend malloc and allocate the size of a node. I want to store the address of this chunk of memory somewhere. And what I'm going to propose is that we have a temporary variable, and I'll call this n, whose type is that of a node star. So what am I doing here? I'm trying to build up this list in memory so that I first have a pointer to the list. I first have a pointer that is null, pointing nowhere. No list exists. I then want to go ahead and create one new node, store value in it, and then point my list at that node. Then I want to do it again and again, a total of 3 times. So how do we do this? We allocate space for the size of a node, however many bytes that's going to be. It's probably going to be 12 because it's 4 for the int and 8 for the pointer. But who cares? Size of will answer that question for me. I'm going to store the address of this chunk of memory inside of a temporary variable called n for node. And that's why it has to be node star, because it's going to be pointing to an actual node. I'm going to do my quick sanity check. So if n equals null, we can't proceed further. I'm going to go ahead and just return 1 right now. So that's just sort of boilerplate code you should be in the habit of doing anytime you're using malloc. But if all goes well, let's do this. Let's go to the address in n, and then go inside of that node and change its number to be whatever the human wants it to be by using getInt and just prompt the human for their favorite number. Then let's go to that same node and update the next field to equal, for now, null, because all I want to do is allocate one new node with that number. That's it. Then I'm going to need to stitch this together further. So I'll propose that all we need do, and let's clean this up first, is now make sure that we string these nodes together. This syntax isn't quite right, because technically, because of precedence, I need to dereference n and then go inside of it. I need to dereference n and then go inside of it. However, this syntax, if it's looking a little overwhelming and you have no idea now what's going on, thankfully in C, there's much simpler syntax, which is this. Go to the node and go inside it to get the number. Go to the node and go inside it to get next. So the arrow notation that I promised we would now have is the same thing as using the star operator, the dereference operator, parenthesizing it, then the dot operator, which is just a pain in the neck to write out all the time. I dare say n arrow number and n arrow next is just much simpler. It says go to n and point at the number field or the next field, respectively. All right. So the last thing I'm going to propose we do, and then we'll make this much more clear in picture form, is this. Let's go ahead and prepend the node to the list. And by prepend, I mean insert it at the beginning, insert it at the beginning, insert it at the beginning again and again. I'm going to say n next equals list, then update the list to set equal to n. And then after all of this mess, I'm going to return 0. OK, this was a huge amount of code, but let me give a quick recap, then we'll paint a picture. Here is my list initially. So the foam finger is pointing to null, which just means the list is of size 0. There's nothing there. Then I ask the computer to do this 3 times. Give me enough memory for a new node. Then, after checking that it's not null, put the user's favorite number in it and update the next field for the moment to null. Then lastly, go ahead and prepend this brand new node to the existing list. And by prepend, I mean put it at the front. So n at this moment is pointing to that new node. And I'm saying, you know what? Whatever the current list is, empty or otherwise, set the next pointer equal to the list, whatever that list is, and then change the list to point at this new node. So now let's do this more carefully, step by step, in picture form. So I'm going to propose that we go through some of these representative lines as follows. Here is the first line of code, even without the assignment. If you just allocate a variable called list, that's a pointer to a node, what you essentially have is a box of memory that looks like this. It's a garbage value, though, because there's no assignment operator, so who knows what's inside of this pointer. That is why, in my actual code, I set it equal to null, which effectively creates in memory the same box, but gets rid of Oscar the Grouch and puts the null value there. So we know it's not a garbage value. It's a pointer known as null. So that's what that very first line of code did in the computer's memory. The next thing I wanted to do was allocate enough memory for a node, not a node star, for a whole node. I want that whole chunk of a rectangle given to me in memory. That's going to return to me the address of the first byte thereof. And I'm going to store that in a temporary variable called n. So at this point in the story, n is going to be a pointer of its own, another box, that initially, sure, is going to be a garbage value. But because I am using the assignment operator, it's going to point to that chunk of memory, which malloc, if successful, presumably allocated for me in the computer's memory. So n, for all intents and purposes, points at that same chunk. These values are still garbage values because it's just a chunk of memory. Who knows what it's been used before? But that's why after this line of code, I took care to get an int from the user and then initialize the next pointer to null. So for instance, for the sake of discussion, let's get rid of getInt for the picture and just say the human typed in the number 1 initially. Well, that's equivalent to putting the 1 in the number field by first going to the address of in n and then dereferencing it using the star and the dot notation respectively. So that means follow the arrow and then change number to the value 1. Then the next line of code, or equivalently, you can just do the same thing. And thankfully, now C syntax lines up with what the pictures look like we've been drawing. Go to n, follow the arrow to the number field. That's literally what the syntax is telling me. Meanwhile, if I use that same syntax again for n arrow next, set it equal to null, that's like saying go to n, follow the arrow, and change the next field, in this case to null, or we'll just blank it out to be clear. So at this point in the story, we have allocated the node. We have stored 1 and null there. List is still null. N is pointing to this. But the whole point of this exercise is to add this node to the list. So we need to somehow update this value, which is why ultimately I'm going to do something like list equals n. Now, that seems a little weird semantically, but recall that n is a pointer. That is the address, pointing at OX123 or wherever that is. So to point list at the same node, it's equivalent to setting list equal to n, because then we'll effectively have an arrow identical from list pointing at that new node. And at this point, I don't even care what n is anymore. It was always meant to be a temporary value. This now is my list. So even though I did it in code already preemptively in a loop, the first iteration for that loop literally created this in memory. All right, let me pause before we go through numbers 2 and 3 for any questions. Because the VS Code version looks scary. This is perhaps a little more bite-sized. No? OK, so how about we do this twice more for 2 and 3 respectively? So again, inside of our loop, we're back to this line, which asks the operating system for enough memory for the size of a node, stores that address temporarily in a variable called n. So here's our friend Oscar brought back onto the screen. Maybe the new chunk of memory is over there. This effectively points n at that chunk of memory. The next line of code inside of that loop that's relevant is this, and we'll get rid of getInt and just pretend that I literally typed in 2. We're going to go to this version of n, follow the arrow, go to the number field, and set that equal to 2. The next line of code, we start at the end, follow the arrow, change the next field to null. And then, same lines as before, we now need to update list equaling n. But something's about to go wrong here. If I update list to point to the same node that n is pointing at, watch what happens. I set list equal to that. N, because it's temporary, might as well go away at this point. But what have I done wrong logically here? Yeah. Yeah, I lost the arrow to the original node. I have orphaned the first node because now nothing in my code is actually pointing at it. I've got in duplication 2 pointers pointing at this chunk of memory. So this thing, even though we obviously as humans can still see it, we have lost track in code of where it is, which means that is the definition of a memory leak. I can never get that back or give it back to the operating system until the program itself finally quits. So I think I need to be a little smarter and not do this line quite like this yet. I think what I want to do, and I've rewound, so list is still pointing to the original list, n is pointing to only the new node. What I think we need to do is something like this. And this is why the code was fairly non-obvious in VS Code at first. Go to n, follow the arrow, go to the next field, and here's the cleverness, point this pointer to the existing list's value. So if the existing list is pointing here, that just means, hey, point this to the exact same thing. Because now I can safely update the list to point at the same thing as n. So its arrow now points here. But even when I get rid of n, I wonderfully have the whole thing stitched together. And the metaphor I often think of is like around like Christmas time and olden times when people would like stitch popcorn together. That's what you're kind of doing with a thread here. You're trying to stitch together these nodes, or popcorn kernels, if you will, such that one can lead you to the next, can lead you to the next, can lead you to the next. But you can never let go of part of that strand in the process. So here now we have a list, which is great because notice we haven't touched the 1, but we've added the 2. We can go ahead in a moment and add the 3, but you can perhaps see where this is going. I'm kind of doing it backwards by accident, but we'll get there soon. So now let's allocate a new node, run through in our mind's eye all of those same steps. I'm going to hopefully end up with a list that now looks like this. And even though it's kind of long and stringy, these values could be anywhere in memory, but because of these various pointers, I can jump from one location to the other, making more efficient use of everything inside of the computer's own memory. All right, but of course, we've got this symptom that I didn't really intend, whereby the whole darn thing is backwards. But I think that's kind of OK for now. But I'd like to propose that we consider how we can now maybe traverse this thing and actually print out the values in memory. So let me go ahead and do this. Let's go ahead and how about let's go back to VS Code here. So at this point in the story, we've got the same code that implements that same idea, except I'm using getInt just so that I can dynamically type in the 1, the 2, and the 3 without having to hard code it into the actual code. Suppose that after doing this exercise, I actually want to do something interesting like print the numbers. Well, we don't have that code yet in this version of my program. So let's bring that back. Last time I did this just using a for loop and array notation. And I think I can do that. But let me propose first that I implement this idea pictorially. Here's the same diagram. This is what exists in the computer's memory. If I want to go ahead and print out these numbers, albeit in reverse order, let me propose that we can do this by giving ourselves another temporary variable. We'll call it PTR, pointer for short. And that's like having another foam finger that points at the start of the list. So it's not pointing at list. It points at whatever list is pointing at which means here. Then I can print out the 3 pretty easily, so long as I next update pointer to point to the 2, print it out, then point it to the 1, print it out, and eventually I'm going to realize, oh, I'm out of nodes because the end of this list is null. So that's the idea I want to implement now logically in code. Create a temporary variable called pointer, set it equal to whatever the list itself is, print out the value, update the pointer, print out the value, update the pointer, print out the value, update the pointer, realize it's null, and stop. So in code, it's a relatively small loop, even though the syntax is still pretty new, since we've only just started playing with memory since last week. But what I'm going to do is exactly what I proposed. I'm going to create a new pointer called ptr and set it equal to the list itself. That's like having another foam finger temporarily pointing at the first element in the list. Then what I'm going to do is say, while that temporary variable is not null, go ahead and traverse the list. What do I mean by that? Well, let's go ahead and print out the current element in the list by using %i\n and printing out whatever the pointer is pointing at, specifically its number field. So that is follow the arrow and print out the number. Then inside of this loop, I'm going to update, after doing that, my temporary variable called pointer to be equal to pointer arrow next. And that will have the effect, with just those few lines of code, of implementing precisely this idea. I first set pointer equal to the list, which happens to point here first. I then do my printf, and then I update the next field. I update pointer to be the value of pointer, follow the arrow, next. So if this is OX123, for instance, that is what is now in, if this is OX456, that is what's now in pointer. So the arrow effectively looks there. In my for loop, I print out with %i this number, and then I go to the next field, follow the arrow, and then set it equal to, whatever this pointer is here, OX789, set it equal to the pointer there. So I effectively move the arrow there. Then lastly, I update ptr to point to the value of this next field, which is null, which means effectively pointer itself is null, which means the for loop cleverly stops now because I was supposed to do this whole loop while pointer is not null, but pointer is now null. And just as an aside, if you prefer the semantics of a for loop, there's nothing new here per se. I can do this exact same thing using a for loop simply as follows. And it's a little tighter to implement as follows. I can say for, instead of int I equals 0 in that old approach, I can actually use pointers in a for loop like this. For node star pointer equals the start of the list. Keep doing something so long as pointer does not equal null. And on each iteration of this loop, update the pointer to equal whatever the pointer's own next field is. And then inside of this for loop, print out using %i\n the current pointer's number field semicolon. So here is where, again, we see the equivalence of for loops and while loops. What you can do with one, you can do with the other. This is a little more elegant in that you can express a whole lot of logic in one line of the for loop. Frankly, I do think the first version is nonetheless more readable. So let me undo everything I just did. On the course's website, you'll see both of these versions. This one's a little more pedantic as to what it's doing step by step. OK, that too was a lot. Let me pause here to see if there are any questions. And if you're feeling like that fire hose, like this is why we transitioned to Python, where all of this now gets swept under the rug, but is still happening, just not by us in a week. Questions? Yeah? Yeah, really good question. So here I've been preaching like we don't want to lose memory, we don't want to leak memory. And here I am fairly extravagantly now spending twice as much memory to maintain this data structure. That's going to be among the themes with all of the data structures we talk about. If we want to gain some benefit, like dynamic growth and shrinking of the data structure, you got to give me something. And what you've got to give me in this case is the ability to use more space. In a bit today, and after break in particular, we're going to decide we'd really like these algorithms to be faster. Well, that's fine, but you're going to have to give me something in return. You're going to have to spend more space to make the code faster. And so time and space and financial cost and human time and any number of other resources are all things that you need to evaluate as a programmer or a manager and decide which is least and or most important to you. And right now, I don't care about space as much as I care about the dynamism that I'm trying to solve first. Other questions on here? Yeah? Yes. Why am I using pointer instead of n? Well, yes, I could reuse n at this point. I deliberately chose to use pointer for two reasons. One, I'm using it for different reasons here. Two, it's not necessarily the best idea to use one variable here for a specific purpose and then reuse the name down here. Besides, it's out of scope at this point anyway. So it just makes me feel better that I have different variables doing different things. But it would not break if I did it your way. Other questions? Yeah, in back. Are pointers temporary? Not necessarily. Like the linked list we are building up in memory exists because we are using pointers to build this data structure and to keep it intact for as long as the program is running. My temporary variables, n and pointer, ptr in this case, those are ephemeral. And I'm only using them to kind of stitch things together temporarily. A good question. All right, so let's now motivate why we're spending so much time sort of stitching these things together so carefully. Well, here's our little cheat sheet of common, but not exhaustive running times. Let's consider what the running time is for some fairly basic operations like inserting a number into a linked list, maybe searching for a number in a linked list or traversing it, and also deleting, ultimately, numbers in a linked list. So here is my list initially, completely empty. And suppose I go ahead and insert the 1, then I insert the 2, then I insert the 3 using code like we just wrote. I love this approach because even though it looks a little scary at first, this is probably the simplest way to implement insertion into a linked list. Why? Because I'm just constantly prepending the next element. Prepending, which means all of my hard work is just here at the beginning of the list. So even if this thing has 1,000 elements in it, I'm only manipulating some pointers all the way over here pictorially at the left, which means it's pretty darn fast. So given that definition in this picture, what would you say the big O running time is of insertion into a linked list when using my current implementation? Big O of 1. Why? Well, it's not literally one step, but it is a constant number of steps, because if we literally counted the lines of code I was executing, it's a few steps to sort of point one thing up here, point the other thing down here, then update the third, and boom, we're done. In particular, what my current code does not care about is the whole length of this list. Why? Because I'm never traversing the whole thing for the insertion part. I am obviously for the printing part, but for the insertion, I'm just prepending again and again. The downside, though, of this approach is that the whole darn thing is coming out backwards. I'm not doing anything with regard to the ordering of these elements, which means what's the running time of search going to be, for instance? If I tell you, search for like the number 1, find it for me. What's the running time going to be there in big O? Big O of, yeah. Big O of n, because in the worst case, it's going to be all the way at the end. And we've seen this scenario before. So it's big O of n for searching. It's definitely big O of n for traversing or printing. But that goes without saying. If you want to print every element, obviously you have to touch every one of the n elements. But what about deletion? Suppose I want to delete an element. That's going to be in big O of also n. Why? Because, again, in the worst case, it could be all the way at the end. So only insertion, as currently implemented, is big O of 1 because we are exercising full control over where the new elements go, irrespective of what the actual values are. So things could escalate quickly here if we do actually want to start keeping things, say, in sorted order, because we can no longer just naively plop things at the very beginning of the list. I think we need to start being a little more careful as to where we put things. So in fact, even though we're doing OK on insert right now, we still have big O of n for the searching and for the deletion, which we won't do in code, as well as, of course, for traversal. So how else might we go about building this list? Well, let me propose that we could maybe append to the end of the list. Let's try that and see if it gets us anywhere better. So here's my list initially, completely empty, aka null. I go ahead and insert the number 1, as before. But now, in this algorithm, I'm going to insert the number 2 and the number 3. So this is great, because now, by chance, it ended up beautifully in order. But that's because I chose the numbers 1, 2, 3. But we'll come back to that detail. Let's consider now what the running time is of this algorithm of insertion using appending to the list. What's the big O running time of insertion now? big O of n. So it's sort of strictly worse because now it's always going at the end. Now, I could be a little smart about it. I could just allocate another pointer and just always have another pointer pointing at the end of the list, just as I have a pointer pointing to the start of the list. That's totally fine if you're willing to spend one more pointer, which is a drop in the bucket, a legitimate solution. But where I'd like to go with this is let's maintain sorted order no matter the order in which the numbers are inserted, whether it's 1, 2, 3, 3, 2, 1, 2, 1, 3, 3, 1, 2. Whatever order the human types in the numbers, I want to build the structure out such that they always end up in sorted order, just so that my contacts in my iPhone or my Android phone, for instance, are sorted as intended. So how do we go about doing that? Well, here we're still dealing with some big O. Let's try this. Here's my list, initially empty. Now the user inserts person number 2 first, so it ends up there. Then they insert number 1. I'd like it to go there. Person number 4, it goes over there. And then person number 3, it ends up here. Even though it's sort of obvious with a piece of paper and pencil how to stitch this together, this is now an annoying number of logical steps because there are so many opportunities where I could screw up and orphan one or more of these nodes. But let's consider the scenarios that we might encounter. Maybe we get lucky and it's like an empty list and we just have to insert one new node. That is trivial. We've done that already. The 2 was super easy to implement. The 1 could be really easy to implement too, because that involves the prepending scenario. And we've seen that prepending is super simple. So there's only 2 other scenarios to consider. Appending, if it's a really big number and ends up at the end, and we've talked about but haven't seen code for that. The annoying one, I dare say, is going to be when the new number belongs in the middle. But I propose to think through it this way because now you just have 4 problems to solve, not just one massive ill-defined problem. You've got scenarios in which you want to insert a new node into an empty list. You want to prepend the new node into the beginning of the list, append it to the end of the list, or somewhere in the middle. So that's like 4 blocks of code in my program. I can now sort of take the proverbial baby steps and implement this bit by bit. And to do this, let me propose that in a moment I'll switch over to VS Code, but sort of Julia Child style, I'm going to open up a pre-made version of the program that actually gives us a working solution, albeit initially with some bugs. So here we have, out of the oven, this version of list.c. At the top of the file, I've got my same includes as before. I've got my same structure as before here. I've again got int main void. I've got the beginning of my list here, setting it equal to null. And then for the sake of discussion, I'm going to insert 3 values for this example, 1, 2, and 3, by allocating enough room for a node, setting it equal to n. Then I'm going to make sure, a sanity check, that n is not null. And then I'm going to actually populate this with the human's first choice of values. So let me scroll down. But as such, there's nothing too new just yet. Here we have the lines of code in which I'm getting an int from the user, setting next equal to null. And then I'm prepending no matter what, per our earlier version that we did on the fly, this new node to the list, and then updating the list to point to it. And then down here, I'm printing the number. So this is where we left off. But this is a pre-made version that's nicely commented. It's on the course's website for reference. What I'm not doing now is intelligently prepending, appending, or plopping the code in the middle. So how do we do that? Let's take a look at this version of the code. So everything thus far is the same. And if I scroll down, besides the new comments, you'll see that now I'm starting to make some decisions after I have allocated the new node and populated its number and next field. As an aside, I don't strictly need to initialize the next field to null because eventually, as we've done in every past example, I've updated that next field anyway. However, because this one might now end up at the end of the list and I just want to program defensively, initializing pointers to null before you're ready to assign their value is a good thing in general. So here's the first of the questions I'm going to ask myself. If the list into which I am inserting this new node is empty, so it's the beginning of the story, super easy. Just set the list equal to the address of that new node, and we're done. That's what happened when I inserted a bit ago the number 2 for the very first time. So indeed, what has just happened here is that now the list, previously empty, contains only a node containing 2. However, thereafter, there was another scenario. So when we moved on in our story and added the number 1 to the list, well, that happened to end up at the beginning, but it could also end up at the end or in the middle. So let's break down those scenarios here too. So here, if it is not the case that the list is empty, in that if condition, we're going to end up here now in the else. What do I want to do here? Well, let's go ahead and for now in this simplified version, append it to the end of the list so we can see that code. How do I do this? Well, I'm using a for loop, much like the one I had before, which just allows me to traverse the existing list, whether it has one node or many. And I'm going to now ask a question. If following the current node's pointer field, next field, leads me to null, aka the end of the list, OK, let's go ahead and update the end of the list to actually equal the new node. So in other words, if I'm sort of following all of the arrows and I reach a node whose next field is null, no problem, update that next field to point to the new node I want to insert. Irrespective of the values, I just want to append this node no matter what, and then I want to break out of the code. Then at the bottom of this version of the program, it's all quite the same, printing out the numbers using the for loop version of my code from before instead of the while loop, but they're equivalent. But what I did do in advance in baking this version of the program is also go through the motions of freeing every one of the nodes afterward. But we'll come back to that. So this version of the code, just to be clear, only appends nodes to the list. It's still not treating things in order. But we've now seen two of the scenarios plucked off. The list is empty, or it has numbers, and we want to put something at the end. So let me propose now that I take out of our distribution code another version of this program that does that and a bit more. I'm going to go ahead and open up in just a moment a new and improved version of list.c. And now it looks almost the same at the top. Scrolling down, scrolling down, scrolling down. Here's some now familiar code. If the list is empty, do that simple thing as before and just prepend it, or rather just set it equal to the list. But here is now where we're adding some inequality. So if the number in question belongs at the beginning of the list, so if the number in the new node n is less than the number in the current list, which is presumed to be the first node at the moment, then go ahead and update the new node's next field to point at the existing list, and then update the list to point at this new node, thereby giving us from 2 in the list to 1 and 2 in the list. To be clear, if I go back to VS Code here, what's happened here is because 1 is less than 2, of course, I'm going to update the new node's next field to point to the list. What does this mean? Well, the new node at this point in the story is the new node for the number 1, because that's the second thing we're inserting. I'm going to update its next field to be whatever the list a moment ago was already pointing at. So this is the after effect. But a moment ago, list was pointing at only the 2. So now the next field of the 1 points at the 2. And then lastly, here in this line, I update the list pointer to be the address of that new node. And here's where I'll wave my hand a little bit today because it starts to escalate quickly. It's useful, and it might very well be useful for problem set 5 in particular, but I think more healthily reviewed step by step at a slower pace. Here is where I'm asking myself, all right, if it's not the only element in the list and it doesn't belong at the beginning of the list, well, it belongs somewhere later in the list, which gives me 2 final scenarios. Let's figure out which scenario we're in. Let's use this for loop to iterate over all of the, as many of the nodes in the list as we need to. If we get all the way to the end, because our pointer variable now equals null, it's like following the arrows, and maybe we're trying to insert the number 5. I've already hit the number 4. I've hit null. 5 belongs at the end. So here we have our promised append code, which is exactly the same as before, but now I'm doing it conditionally if I've indeed found my way to the end of the list. And then lastly, let me scroll down just a little bit. If it's not the case that the list is empty, and it's not the case that the new node belongs at the beginning, and it's not the case that the new node belongs at the end, I'm just somewhere in the middle of the list because the new number I'm inserting is less than the one I'm looking at here. And it's OK to use 2 arrows, but I'll wave my hands at that for now. These 3 lines, 2 pointer manipulations and a break, is what's going to stitch together that 3 in between the 2 and the 4. And let me propose for lecture's sake, take this on faith that this collectively does stitch things together properly. But I do think, as you'll see in problem set 5, it's a much better exercise to think through a little more carefully step by step, because there's just a lot of fine-tuning of these pointers together, and the order of operations does matter. But at the very end of this program, notice this is kind of mindless, even though the syntax is undoubtedly less familiar. Here is how, just like traversing the whole list to print it out, we can similarly do one more pass over the linked list and free every one of the nodes. But notice it's not quite as simple as just saying free the whole list. Free is not that smart. Malloc is not that smart. And even though you have called malloc 1, 2, 3 times, you have to really call free. You have to call free 1, 2, 3 times. You can't just pass at the beginning of the linked list and say you figure out what to delete, because it has no idea what a linked list is or what your data structure actually is. So the reason that this loop is a little complicated is that what I'm doing with these 3 lines is essentially traversing my list and making sure that I have a pointer that when I'm ready to delete the 1, I have a pointer pointing at the 2, and then I free the 1. I update my pointer to point at the 3, and then I delete the 2. I update my pointer to point at the 4, then I delete the 3, and then I delete the 4. So there's a bit of trickery involved in making sure you don't orphan things step by step. Whew. OK, that was a lot. Let me pause here to see if there are, in fact, any questions, even though we're deliberately waving our hands at some of those details. Questions on this? No, let me add one final flourish. If we were to really quibble over this, I mean, my God, we're up to 80 lines of code already just to implement the numbers 1, 2, 3, 4. But there are some subtle bugs in here at the moment. So for instance, suppose that something goes wrong with malloc inside of this for loop here. And suppose that it's not your first iteration. Something goes wrong on maybe the second or the third iteration. Why is this error check suddenly bad as I've implemented it? Yeah. I didn't free the memory from the previous iteration. So this is where memory management starts to get really annoying, because if you do want to practice what I've been preaching, which is free any memory you've allocated, and you've already allocated 1, maybe 2 nodes, because malloc is, again, failing maybe at the last iteration here, you have to somehow go back and free all of that. And that's fine. Like, we have code at the bottom of my file here, which could traverse through the existing list and just free it all. So I could just copy, paste that code, put it into my if condition, and then run that code too to delete the whole list. But at this point, if you're copying and pasting, you're probably doing something wrong. And so let me propose as a final version of this, just for your reference later, in the 9th and final, in version 9 of this file here, 0 indexed, what we have, give me 1 second to just make a quick copy and copy it over. In list9.c, our last version of this, we have the following, whereby now, in my function, in my main function, I have the exact same code as before, but I've taken the liberty of implementing an unload function so that I can call it here as well as at the bottom of this main function. So I can unload it here or unload the list there. And all I've done now is, in good form in terms of design, just implement the notion of deleting a linked list in its own function, so I can call it any number of times from any number of places. But just so you've seen how I might do that there. All right, so let's ask the question, after all of this, what is the running time of inserting into a linked list? Big O of, say it a little, big O of n. Damn it, like, that's no better. All right, what's the running time of searching a linked list? Big O of n. Damn it, what's the running time of deleting from a linked list? Big O of n. So like everything is literally big O of n. So there's the price we've suddenly paid. We have, an hour after we started with arrays, gotten to the point where we can dynamically grow in a linked list. And I dare say, even though we've not done it and won't do it today, shrink the linked list by freeing things that we don't need. So we have the dynamism, and we can make more efficient use of memory, even if it's very fragmented and there's a few bytes here, a few bytes there. But we've paid this price because with arrays, recall, even our phone book example, we at least had binary search, the running time for which was big O of log n. So my God, not only are we spending more space, the darn thing is slower. Surely this is not how our phone contacts are implemented. Surely this is not how stacks and queues are always implemented. And indeed it's not. This is just going to be a stepping stone to now doing a sort of mashup of data structures whereby we take the best features of arrays, the best features of linked lists, mash them together to get new and improved data structures. But for that, we're going to have some cookies first, and we'll come back in 10 minutes. Cookies are now served. All right, we are back. So let's recap how we got here and why. So we started with our old friends arrays, which we introduced in week 2. And recall that the whole appeal of arrays was that, one, as all things go, like relatively simple, certainly now in retrospect. But more importantly, they were really darn fast. Like arrays, insofar as they are stored back-to-back, contiguous in memory, means that we could do very simple arithmetic, recall, to like figure out the length of it, and then divide by 2 to get the middle, divide by 2 again to get the middle of the middle, and so forth. And even though we might have to deal with a little bit of rounding, arrays lent themselves to binary search and thus logarithmic time, so big O of log n. But today I claim that the downside of arrays is that you have to decide in advance how big you want it to be, and if you guess wrong and it's too small, how much memory you ask for, you then have to reallocate memory, and that's fine. It's solvable with malloc or realloc, but it's going to take some amount of time to copy all of the old memory into the new memory, whether you do it with a for loop or realloc does it for you. Meanwhile, we only did it with like 3 values, maybe 4, but imagine it being 3 million values that you now need to allocate more space for. You're going to waste a huge amount of time copying 3 million values from the old location to the new, and so that's just generally not very appealing. And so that motivated our whole discussion of linked lists, whereby now we can create a more dynamic data structure whereby we only allocate memory as we need it. So we don't have to worry about underestimating or overestimating and therefore wasting memory. We can just go bit by bit for each new value. We allocate another node, another chunk of memory, and the thing just grows and grows and grows. But as we saw just before break, the downside is even though we're avoiding the inefficiency of having to move stuff around in memory, once allocated, the nodes can stay where they are, and we just update our pointers. All of our running times for searching, inserting new elements, deleting old elements would seem to be big O of n. But why was that? Well, in the context of a linked list, recall that it might look a little something like this, whereby we have a pointer called list pointing to maybe 4 values like this. And suppose that we do want to search for a value. Now, it's nice because in our latest version of this linked list, it was sorted from smallest to largest, and that was always a precondition of doing binary search. But even though it's obvious to our human eyes where the middle is, it's like roughly over there, how is the computer going to figure that out, or how is your code that you write? Well, unfortunately, the way we've stitched a linked list together with these pointers is if you want to find the middle, you can, but you got to start at the beginning, traverse the whole thing to figure out how long it is, then do it again and stop halfway through, once you know what the halfway point roughly is. Then if you want to search the middle of the middle, you've essentially got to do that whole process again. And so now, just to use binary search, you need to spend big O of n steps just to even find the middle. Now, if your mind is kind of spinning and you're like, well, maybe I could just kind of cheat and use a pointer to always point to the middle of the list, totally fine. You can spend in some additional space to remember the middle of the list, the end of the list. But where does that stop? What if with binary search you go not just to the middle, but the middle of the middle, the middle of the middle of the middle, the middle? Are you going to keep around a pointer to every element? Because if you do, you're essentially back to an array if you've got one location for every other location. So it just kind of devolves into a mess, even though there's some minor optimizations we could in fact make. In fact, we didn't talk about it yet, but one common alternative to a singly linked list, which ours is, it's linked with a single pointer from node to node. Computer scientists also like to talk about doubly linked lists, where there's arrows going both directions, which actually would have simplified some of the last code that we looked at, because I don't have to look ahead to figure out what I want to free or what and where I want to insert some value. But that too doesn't fundamentally change the speed. It just makes your code a little easier to write. So in short, with linked lists, we get dynamism. We can now grow and shrink things without wasting time copying, but we've lost hold of our binary search. And that was very appealing as far back as week 0 when we wanted to do something quite quickly. So let's see if we can't make some mashups now. Take some arrays, take some linked lists, literally mash them together into a sort of Frankenstein data structure and see if we can't get some of the speed of arrays, but the dynamism of linked lists. And so I give you trees. If you think about in your mind's eye what a family tree looks like, where you typically have some parents and then some children and some grandchildren and so forth, it's this sort of tree-like structure, even though by convention it's drawn top down instead of bottom up like trees in the real world. But the top of that family tree we're going to call the root of the tree. It just so happens to indeed grow down. But a tree is a very common data structure And it's interesting vis-a-vis arrays and linked lists in that it's the first of our two-dimensional data structures. An array is effectively just a single dimension along from left to right. A linked list is essentially the same, even though in reality it might be up, down, left, and right in memory. It's still just one thing stitched together in a single dimension. A tree adds now a second dimension. And specifically useful for us is what we're going to call binary search trees, which is, spoiler, going to give us back the ability to use binary search. But we're going to store the data a little more cleverly than in arrays alone. Instead of storing our data in one dimension, in a binary search tree, we're going to store it in effect in two different dimensions. And that's going to gain us some speed. So here, for instance, is an array of 7 numbers, as we might have seen it back in week 2 when we first introduced arrays. Let me draw our attention to the middle element, and then to the middle of the middles, and then the middles of the middles of the middles, just by color coding them slightly differently. If I were to run binary search on these numbers or the lockers that we had on the stage a few weeks back, I would jump to the middle, then the middle of the middle, and so forth. The catch, though, is that implemented as an array, it's not going to be very easy to add new values. Why? Because if I want to add the number 8 or 9 or 10, I might get lucky, and there might be room in memory here. But I might get unlucky, in which case then we got to start jumping through those hoops of malloc or realloc and copying all of this memory to a new location, which is doable. We solved it in code, but it's going to be slow for larger data sets. So can we avoid that? Well, maybe. I deliberately color-coded things like this because let me propose that instead of storing these 7 values in an array, let's store them in a family tree-like structure like this, where I just kind of exploded them vertically on the y-axis here. So now the middle element, the 4 is at the top of this tree. The 2 and the 6, which were the middle elements after the middle, are going to be to the left and right of the 4. And then these leaf nodes, so to speak, we borrow a lot of vernacular from the world of actual trees. These are leaves in the sense that they themselves have no children. They're at the edge of the data structure, are going to be the middles of the middles of the middles. But all of the data is still there. I've just exploded it from 1 to 2 dimensions. And let me propose that now that we have this technique of using pointers, which we use with C code, but you can depict them pictorially with arrows, let me propose that we stitch together these 7 values in memory using a bunch of pointers, whereby now each of these nodes, drawn as a single square for simplicity, is going to have not only an integer associated with it, and not just one pointer, but per these arrows, as many as 2 arrows associated with it. So our nodes are about to go from data structures with 2 things, a number and a pointer, to 3 things, a number and 2 pointers for the left and right child, respectively. And I dare say now that we have a 2-dimensional tree data structure, consider how you might find a number therein. Suppose I'm searching for the number 5. Well, I start at the root of the data structure, and even though our human eyes obviously know where we're going, notice what's important about this binary search tree. If I go to the root of the tree, I see the 4. 4 is obviously less than 5. What does this mean? This means I can divide and conquer the problem right off the bat. I know that 5 is going to be to the right of this node, which means effectively, if you think in your mind's eye about snipping the branch there, I have just halved the problem, essentially, like dividing the phone book in half. Why? Because I don't even waste time looking at this subtree, the left child of the 4 element. Meanwhile, if I go from the root to its right child here, I see the number 6. 5, of course, is less than 6. So this is effectively like snipping off that child because I don't need to go further there because I know a smaller element is going to be in this direction. And that's the key property of a binary search tree. It's not just a family tree with numbers all over the place. They follow a certain pattern. Every element is going to be greater than its left child and less than its right child, assuming you don't have identical values. And that property is actually a recursive one, to borrow terminology from a couple of weeks back. Recall that a recursive function is one that calls itself. A recursive data structure, like the pyramid in Mario, is a data structure that can be defined in terms of itself. Well, a binary search tree is a recursive property insofar as if it applies to this node, it also applies to this node. Case in point, 2 is greater than 1, but it's also less than 3. It's true over here. 6 is greater than 5, but less than 7. And it's technically true of the leaf nodes because the definition is at least not violated there because they don't even have children themselves. So this is a binary search tree because of that pattern. So this then invites the question, well, how long does it take us to search for a value in a binary search tree? Well, if the number is 5, it's going to take me 1-2 steps. But if there's n elements here, can someone want to generalize that, either mathematically or just instinctively? Big O of log n. And even if you're not quite sure how the math works out, anytime you take a data set and you have it, we're talking about log base 2 of n again. And indeed, that's going to describe the height of this tree. The height of this tree is essentially log base 2 of n, because if n is 7, it's going to give me essentially 2 when we round appropriately. If we round up, if we've got 8 elements, log base 2 of 8, 2 to the third, so that means 3. So 1, 2, 3. It kind of works out, even if I'm doing that a bit quickly. The height of this tree is log base 2 of n, aka big O of log n. How long does it take to insert? I think it's going to take log n because I can insert over here or over here or over here, depending on where the number goes. How long does it take to delete? I'll claim it's going to take about the same. So wow, we're back in business. I've got now the ability to grow and shrink my data structure, because if I want to insert the number 8, it's going to go right there. If I want to insert the number like 5.5, I can see where I would put it. It's going to be easy to add new nodes by just updating the pointers without copying everything in memory like we had to for arrays. But there is a downside here. I got to concede something. What price am I paying? What's the trade-off here? To gain that dynamism and that speed, but yeah, I'm literally using 3 times as much memory now, because even though it's not depicted here explicitly, each of these squares represents an integer and a pointer and another pointer. So that's like 16, that's like 20 bytes at this point of memory, instead of just 4 bytes for each of the integers in an array. Nowadays, though, space is pretty cheap. We all have very large Dropbox folders, iCloud folders, and the like, so it's not really a big deal to use that many more bytes. Certainly not a big deal for 7 numbers, but if it's 7 million numbers, maybe this isn't the best data structure to use, even if speed is important. You got to decide ultimately, based on your actual use case, what matters more. So in short, a binary search tree you can kind of think of as an amalgam of, or rather a variant of, a linked list, except that every node has as many as 2 pointers instead of 1, which is what gives us now this second dimension. And in fact, this translates pretty nicely to code. In fact, if we consider how we implemented in a linked list a node, recall that it looked like this, where you got a number in each node and a pointer to the next element in the linked list. Well, I think for a binary search tree, we can sort of borrow this as inspiration, make a little more room, because we need 2 pointers instead of 1. And I'm just going to call the left child the left pointer and the right pointer. But here is the 3 times as much space, give or take, because I now have 3 elements associated, 2 pieces of metadata and 1 piece of data that I actually care about to stitch this thing here together. All right, well, if this is the data structure there, how could I implement this in code? Well, here's where recursion again comes into play. The fact that a binary search tree is recursive in nature, in that what you say about this node, about it being greater than the left child and less than the right child, can be said of this node and this node and this node and this node. You can leverage that beautifully in code like this. So suppose I'm implementing a search function in C whose purpose in life is just to say yes or no, true or false, the number you're looking for is in this tree, which might be a useful thing to check in an algorithm. Search is going to take 2 arguments, I propose, the number you're searching for and a pointer to the tree. That is the root of the tree initially. So how do you actually traverse this thing in C code? Well, we can pluck off the easy case first, the base case. If the tree itself is null, like if you hand me nothing, I'll give you your answer right now, false. Like there's no number here if the tree is empty. So that's easy. Otherwise, if the number you're looking for is less than the number in the current node. So tree is what's passed in, a pointer to the root. So if you follow the arrow, you can get inside of that value and see its number. If the number you're looking for is less than that, OK, you want to snip off the right tree and dive down the left subtree. So you search the tree's left child for the same number. Else, if the number you're looking for is greater than that number, you search for the tree's right child for that same number. And the fourth and final scenario is what? Well, if the number you're looking for equals the number in the current node, you got it, return true. And if you recall some of our past design discussions, this is sort of a waste of everyone's time to ask this question explicitly. Let me tighten this up design-wise, because there's only 4 possible scenarios. Either there's nothing there, it's to the left, it's to the right, or you found it. It's right there. So whether or not you agree at this point in your programming career, like there is a beauty to this code that most programmers would claim is here, and that it's so relatively elegant, whereby you've defined what the function is. You've got this base case, which is arguably one of the clunkiest parts. But the fact that you can just check a value here and then traverse the exact same structure, but a subset of it by traversing the left subtree or the right subtree is like a beautiful application of recursion. And it allows you to search for this thing no matter where it is in the computer's memory. Questions then on this idea of a binary search tree or this actual code thereof?
But if you don't ask the question, if the number is not there, it will return true either way.
Nope, if the number is not there, we recall, so if we get all the way to the bottom of the tree, such that now I'm at one of those leaf nodes, and that's not the number I'm looking for, such that there's no left child left, no right child left, this conditional is going to kick in, and I'm going to return false. But if I find it along the way, whether it's at the top of the tree or somewhere in the middle or among the leaves, I will eventually return true. Good question. And to be clear, even though I'm calling this a tree, that's true certainly for the first time I call this function, because I'm passing in a pointer to the whole tree structure. But if you think about it, what's the left subtree and the right subtree? It's just a smaller tree. It's like a baby tree that's attached to this parent node, so to speak. So it's perfectly reasonable to just call the search function with that child, because it in turn has a whole subtree below it, or the right child, which has the whole subtree below it instead. All right, so I like this direction. We've now kind of improved upon linked lists. We've gained back some of our performance because we can now find something with big O of log n time. I don't love the fact that I'm using 3 times as much memory roughly. That feels like kind of a high price to pay just to speed things back up. But let's consider whether or not this thing's actually going to work as the data structure gets bigger and bigger as well. So it looks beautiful here as written, and that's deliberate because I drew the picture like this, and it's got 7 elements in it. But how did we get to 7 elements? Let's start from the beginning. Suppose that the tree is initially empty, and suppose that a human, using getInt or some other technique, inserts the first element into the list, like the number 2. And the goal is to maintain the binary search tree property, which means you got to have it greater than left child, less than the right child. So suppose the human, using getInt or some other technique, next gives me the number 1. No big deal. I plop it right there. Is the left child, suppose they give me the number 3 next. No big deal. It goes right there. I have very deliberately manipulated this story to work out beautifully, such that the tree is smaller, but it's still a binary search tree and nicely balanced, so to speak. But what if the user, for whatever reason, just gives me a more perverse sequence of inputs, like the worst case scenario, to give me 3 elements? And suppose they give me 1 first. OK, that's the root. Then they give me 2. OK, that's cool. That's like the right child. But what if they then give me 3? Well, to maintain that binary search property, the 3 has to go over here. Suppose perversely, then they didn't give me 4, then 5, then 6. Imagine in your mind's eye where this story is going. What have I accidentally created in memory then? A linked list, which is like bad for all the reasons we discussed before the break, because even though we're getting the dynamism, it's devolving into big O of n. So I've kind of manipulated the situation here with their original example with 7 elements and then 3 elements by making sure that they were inserted in just the right order. Because unless you are clever about how you build the tree in memory, it could very well devolve from a tree in 2 dimensions into actually a linked list in 1 dimension. And now this is just a long and stringy tree that does not violate the binary search tree definition, but it is surely not balanced in this case. Now, as an aside, if you take higher level languages and data structures and algorithms, there's many different alternatives to binary search trees that actually have baked into the algorithms a little bit of rejiggering of the structure, so that really, as soon as you insert this 3, you spend a little bit more time and clean the situation up. And essentially what you do is like pivot the thing around this way so that 2 becomes the new root, and then 1 hangs off of it, and 3 still hangs off of it. So with each insertion or deletion, you rebalance the tree as needed, which does cost you a bit more time, but it avoids the thing devolving into big O of n again. And we won't do that in code, so this is recoverable, but not if you implement it naively, as I did, at least verbally, in this story. All right, well, can we do better than that? Well, why might we want to? Well, at this point in the story, It certainly could devolve into big O of n, and that's not great, certainly for large data sets. It's nice that we're back to log n, at least if you take on faith that we could kind of rebalance this thing as needed and maintain a logarithmic height for it. But really, the holy grail of data structures is to achieve something that is big O of 1, like constant time, whereby no matter how many numbers or names or sweaters are in the data structure, it will take just 1 step, or maybe 3 steps, or heck, even 100 steps, but a number of steps that is completely independent of how many actual pieces of data are in the data structure. That is to say, over time, it doesn't get any slower, even if you've got tens, hundreds, thousands, millions of elements in there already. So how do we gain something like big O of 1, constant time? The appeal of which is reminiscent of our early picture from week 1. Like, this was our early algorithm for finding someone in a phone book or counting students in the room, something linear, literally straight lines. This was the logarithmic curve, which, especially as you zoom out, starts to get very, very appealing time-wise. Something that's constant time looks even prettier. It is a straight line at like the 1-step mark or the 2-step marks, whatever the constant number of step marks is. And even though logarithmic will still grow in perpetuity, constant time, by definition, never changes. And this is what we'd really like. So when you're searching for someone in your phone, you're searching for something on Google, you're asking a question of ChatGPT, you get an answer like that in constant time, independent of how much data is actually in there. Well, let's see how we can do this. To do this, we're going to at least need a new building block, a term of art known as hashing. Hashing sort of formally takes an infinite domain of values and maps it to a finite range of values. So from high school math class, domain is the input, range is the output. So an infinite domain to a finite range is the goal here of hashing. And we might see this actually in the real world when you're playing, games or whatnot, or you're cleaning up after a game. Like here are some super jumbo playing cards that we got online. And suppose that you want to just get these into sorted order. You could do this very painstakingly. There's 52 cards here. You could kind of lay them all out and start sifting through them and put the 2 over here and the 4 over here and the hearts and the clubs and so forth. Or you can start to look at the cards and bucketize them first to take a 52 size problem and maybe shrink it down into 4 13-byte problems. So here, for instance, is where the first diamond might go, the club here, spade over here, diamond over here. And I can kind of just do this again and again, bucketizing, literally, all of these values so that I've got a very simple heuristic that allows me to move the cards into these buckets, each of which is going to have a subset of the values. And then I've got smaller problems I can deal with. So ... assume that I bucketize all 52 of these values. Then I've just got 4 problems remaining. And I dare say it's a little easier then because they're all of the same suit. And so I can pretty easily sort it from ace to king or whatnot, because those are effectively just numbers at that point. So hashing refers to, again, taking values from an infinite range. In this case, it can be finite, and it is in this case. But if you were doing it more generally with numbers, you just have to map it to a finite range, like 1, 2, 3, 4, finite number of buckets of values, at which point then you can solve the problem a little differently or a little more efficiently. So why is this germane? Well, I would propose that if we want to start organizing our data in memory toward an idealistic goal of achieving constant time, hashing might be one ingredient for the solution there too. And generally, we're going to describe the process by which you decide what input goes to what output is namely what's called a hash function. It's a mathematical function or a function in code that takes as input a card from a deck or maybe a word from a dictionary and outputs a value that represents the bucket into which it should go. So in the case of our contacts app, for instance, of course, in the GUI of it, you have all of your friends and family top to bottom, alphabetically, presumably. You might want to ideally find someone quite quickly, ideally in constant time. Right? The naive implementation that Apple or Google could implement is just use linear search. Search through all of your contacts, top to bottom, and eventually you will correctly find the person. But wouldn't it be nice if they instead use an array, and then they can use binary search and get you the person in logarithmic time? That's great. But if you have a lot of friends and family in there or a much larger data set, wouldn't it be nice to just jump to the answer in 1 step instead of even log of n steps? So that's our goal. Can we get close to or actually at constant time? So with the hash function, we essentially have our old friend problem solving here, the inside of which the algorithm is known as a hash function. And for instance, if I'm looking up Mario's number, I might now want to look for Mario, not top to bottom, or not divide and conquer, jumping around to the middle of the middle of the middle. Let me just figure out what bucket Mario is in. And in the English alphabet, there's 26 letters of the alphabet, A through Z, either uppercase or lowercase. And suppose that I want to find what bucket Mario is in. Well, much like these cards and the suits thereof, wouldn't it make sense that anyone whose name starts with A goes into the first bucket, and maybe the B's go into the second bucket, and the ... Z's go into the last bucket? So it stands to reason that if I pass in Mario to a hash function implemented in C or some other language, I would like to get back the number 12, because M is the 13th letter of the alphabet. But if we start counting at 0 with our buckets, which are essentially an array, then it's index location 12 instead of 13. Similarly, if Luigi is the input, I'd like to get back the number 11. So my hash function somehow takes as input in this story a string and gives me an integer. I claim there's theoretically an infinite number of names in the world in the English language, but there's only going to be 26 possible answers from this hash function, 0 through 25. So that's our infinite domain to our finite range. Instead of 4, it's now 26. All right, so what should we do with the computer's memory to leverage the fact that we can very easily bucketize names based on the first letter of someone's name? Well, let me propose that the hash function part of this, arcane as it looks, is actually pretty straightforward. So if you wanted to translate this idea into C, you can include ctype.h, which we've used a few times to get at access to functions like toUpper. And this is just to make sure you can be case insensitive. Here's my hash function. It's going to return an int, which is the goal. Takes a string as input. We'll call it name. And what does this function do? Well, it's kind of some clever ASCII arithmetic. It first converts to uppercase the first letter of that person's name. So if it's in all lowercase, forces it to uppercase. Why? Because I want to subtract no matter what 65, aka the ASCII value of capital A from this. And I don't want to screw up the math if I'm doing a lowercase letter minus a capital. I want capital minus capital is all. So this will return to me a number between 0 and 25 inclusive. Because if it is a name that starts with A, I'm only looking at the first letter. I'm subtracting off A. That gives me 0. And I'm going to return 0 as a result. ... If it's Z, I'm going to return 25 instead. Now, there's no error checking in here. If you type in non-English symbols, it's going to break. So let's just assume for simplicity this is indeed an English name that's coming in. I can refine this a little bit. I'm going to propose moving forward in our final week here of C, there are some added defenses you can put in place when writing code. Like if you know that you're receiving a name as input, that is, you're passing something in by reference, there's a danger now, per last week, because now the caller of this function, whoever's using this function, is telling you where to find Mario and where to find Luigi's name. The problem with that is that you could go to that address and actually change their name in memory, even if you're not supposed to. You're supposed to just use the name. So you can do something like const, which says you should not be able to change this value, even though I'm not giving you a copy of it by value. I'm giving you a reference there too. Another refinement here is that a hash function for an array as the goal should return a value that's 0 or 1 or 2 on up, never negative. So we can even more protectively say it's not just an int, it's an unsigned int. And we talked briefly about that last week, albeit in the context of chars. These are just minor improvements that makes your code arguably better designed because you're opening yourself up to fewer possible mistakes or issues. All right, so with that said, let's now assume that we've got this kind of function implemented, and we can now use it to decide what bucket to put these people's names into. Well, let's give you what are called hash tables, which are sort of the Swiss Army knives of data structures, the kind of thing that some computer scientists have been quoted as saying if they were stuck on a desert island with only one data structure, this is probably the one they would want. Why? It's just really generally useful because it allows you quite powerfully to associate keys with values, which is to say, to come full circle today, hash tables are often how you would implement at a lower level the thing we began class with, talking about dictionaries, collections of key value pairs. That, after all, is what a phone book is. We call it, names and numbers, but it's keys and values. That's what an actual English dictionary is. The Oxford English Dictionary, it's a bunch of words and definitions or keys and values. So useful in general to be able to associate one piece of data with another. Ergo hash tables. So here's how you might implement in C a hash table. You want it to be of size 26, for instance, so 26 buckets from A to Z, hence the 26. You want this to be an array, and that's fine. This is an array of 4 buckets. I'm going to use an array of 26 buckets because a hash table, too, is going to be an evolution of our linked list mashed together with an array. So a hash table, in short, is going to be an array with linked lists. as we'll soon see. Here's the array, 26 pointers to nodes. So I'm going to give myself an array of pointers that is going to store ultimately a whole bunch of person objects like this. So for instance, here's a char star name, char star number, as we've discussed in the past, representing a person. These are the pieces of data I might want to store in this data structure. However, let's simplify it. Let's not worry about the phone number because we're not going to call anyone today. But for a linked list of persons, I'm going to need to store, let's say, the person's name, but also a pointer to the next such name, to the next such name, to the next such name. So again, I'm just deleting number as being unnecessary detail. But if we're going to have an array of linked lists, this is our new definition of node for this part of class, whereby it's not for a tree, it's now for a hash table. And we'll see this in action now. Here's my array of size 26. I drew it vertically, but who cares? These have always been artist renditions thereof. It just fits nicely on the screen this way. This is location 0. This is location 25. So any A names should end up over here. Any Z names should end up down here, and so forth. Let's just generalize this away as letters of the alphabet for clarity. That's where all of the names are going to go. So hopefully Mario here, Luigi here, and everyone else. So what are each of these squares? They're just pointers to nodes. Initially all null, all claim. But as soon as I insert Mario into this so-called hash table, I'm not going to put him literally here. I'm going to create a new node in memory, put Mario there, and then stitch it together. Because if I get another M name, I'm going to stitch it together and together and together again. So for instance, here comes Mario into this data structure. So this is a pointer to a person structure. Here's Luigi, and here's a third character as well, Peach. That's all working out great. Dot, dot, dot. There's a whole bunch of characters in the Nintendo universe. Here's a lot of them. Unfortunately, especially if you're a fan, there's also other names that do start with M and L and other letters of the alphabet. So we're poised to have what we're going to call collisions, which is a downside of using a hash function. If you're going from something infinite to something finite, by definition, you're going to have a heck of a lot of potential collisions somehow. Multiple M names, multiple L names, and so forth. So we've got to mitigate this somehow. Well, if you meet someone in the real world whose name happens to start with M and you already are friends with Mario, well, you could delete Mario from your phone and put that new person there, but that's kind of dumb. You could clobber the value, that is. Or maybe you put the M friend here, and when that fills up, you put the M friend here, and then when you meet someone else whose name starts with M, you put it here. But then it just devolves into this mess, at which point now there's no rhyme or reason as to who is where. It devolves back into something linear. If you have to search the whole darn thing looking for M friends just because you ran out of space where you want it. So here's the beauty of mashing together an array with a linked list. You hash the name to the intended location, like box 12 here, and then you just start stringing them together in a linked list. And hopefully you don't have too many of those collisions, but at least now you don't have to delete or make a mess of the data structure. So here's another bunch of names, 3 starting with L. Here's a bunch for the other letters of the alphabet. And it's just it's an array now of linked lists. This then is a hash table. So the question to consider now, is this better than an array? Is this better than a linked list? Well, I dare say it's better than a linked list, because if it were a linked list from A to Z, what would be the running time of searching for anyone? Well, I'll spoil it, big O of n, because even if it's alphabetically sorted, you got to start at the beginning and go all the way through the list potentially to find someone like Zelda whose name starts with, of course, Z. But here we have an array of linked lists. So what's really the running time here? It's not quite as bad as n steps, because if you assume a uniform distribution of names such that the world of Nintendo maybe has as many M names as L names, as A names, as B names, you could assume that there's a bunch of chains, a bunch of linked lists here chained together, but they're all roughly the same. So maybe you have n names in your phone book this way, but these lists are only of size, they're only 1/26 of that length, because you've got that many names there. So what's the running time? Well, ideally, we'd move away from linked lists with big O of n and achieve our constant time, but we have these collisions to worry about here. Just to be clear, we want to get from big O of n to something constant time, but we're not going to get to constant time if we've got collisions. If we've got 3 L names and a few B names and a few A names, we can't just jump to that location and find the person we're looking for. So what's the fundamental goal? Well, I think we want to maybe use a smarter hash function. And here depicted is an excerpt from a bigger hash table that is a much bigger array that assumes that you're not looking at the first letter of everyone's name, but apparently what instead? the first 3 letters of the person's name, which just decreases the probability of collisions. Because in this model, I dare say there's no one else's name in the Nintendo universe that starts with L-I-N. So now Link has its own location in memory. And similarly for Luigi, L-U-I, I believe, is unique in the Nintendo universe, so we don't have a collision. Unfortunately, while this does seem to eliminate collisions based on this tiny example, what's the trade-off? Or what's the catch? Yeah. This is a lot more memory. I mean, kind of hinted at the fact that I didn't even fit most of it on the screen anymore. Here's L-A-A, here's L-U-G, but what about all of the other letters of the alphabet and the other combinations of ... all possibilities? Moreover, some of these just don't make much sense, at least in English or in the Nintendo world. I don't think there's anyone whose name is going to start with AAA or AAB or AAC or AAD or AA and so forth. We're wasting a huge amount of space to reduce the probability of collision. So that's fine. We might get constant time now, but at what cost? Well, a heck of a lot more memory. And so this is one of the tensions when using a hash table is you want to come up with a good hash function that's maybe a little more sophisticated than the first letter, but not so wasteful that you need a crazy number of buckets and therefore a huge amount more memory. So really, even with collisions, it's not quite as bad as n steps, because technically if you have k buckets, where k is like 26 buckets, or 4 in this case, technically if you do assume that the names are uniformly distributed over A through Z, the English alphabet, well, each of those linked lists is going to be hopefully no bigger than n divided by k, so n divided by 26. But what do we know about higher order terms when doing big O notation? Big O of n divided by k, yes, it's faster, but asymptotically, that is theoretically, you're still talking about big O of n. So here's a tension, though. Like, it's absolutely going to be faster. It will be like 26 times faster than a linked list, but it's still just big O of n, because it's going to take an amount of time that's still linear in the size of the data set. So we seem to have strayed yet again away from our constant time search. So can we find this holy grail? Well, we kind of can if you let me spend just like a lot more space. There are tries in the world, which weirdly is short for retrieval, even though we don't say retrieval, but a trie is a tree made out of arrays, right? So at some point, computer scientists were just like mashing things together Frankenstein style, like linked lists and arrays, and now we've got trees and arrays. You too can mash something together and come up with your own, but let's look at what a trie actually is, because it is going to get us that constant time grail. So here is the root of a trie. You can think of each node in a trie as really being an array of values, A through Z in the case of an English problem like we've been playing with here. And what you do is you treat this array as being indexed from 0 through 25, or equivalently A through Z, and you treat each of those elements as a pointer to another such node in the trie. And what you do is implicitly store the names that you're storing in this data structure by going to an appropriate location based on the first letter in their name, and then adding a pointer that represents the second letter in their name, adding a pointer that represents the third letter of their name, and so forth. So what do I mean by this? Suppose we want to insert Toad, one of the characters from the Nintendo universe, first. If we count up where T is in the alphabet, this pointer here will be changed from null to a pointer to a new node that represents the second letter in Toad's name, which is going to be, of course, O. Then to insert TOA, we're going to need another node. A is going to lead me to D. And for depiction's sake, I'm going to draw it in green, even though this would actually be a Boolean or something like that in memory that indicates that Toad's name stops here. So in other words, this trie in memory has 4 nodes now. Each of those nodes is essentially an array of size 26. But the word Toad is not actually stored in the data structure explicitly. There's no char star Toad, but implicitly, because the T pointer is non-null, the O pointer is non-null, the A pointer is non-null, and the D pointer is in fact null at this point, is the common technique here. This allows me to insert other names from Nintendo's universe, like Toadette, because I can continue from here to go to the E node, to the T node, to the T node again, and an E node, which I'll again mark in green. So you can even have names that are substrings, or equivalently superstrings of each other, by just having all of these various breadcrumbs along the way, where again, a non-null pointer here to a non-null to a non-null to a null pointer here indicates that or it can't be null at this point. This is where we have to use a Boolean. Indicates that there is a name in this data structure that ends here, and there's another name that ends here. Meanwhile, if there's a third name from the universe, like Tom, same idea, but eventually we can start reusing some of these arrays whereby non-null, non-null, null, or there's a Boolean flag here that says true, a name ends here. Now we're reusing that same array. So each of the nodes represents the ith letter of the word or the name you're trying to store in the data structure. And by playing around with null and non-null and some Booleans, you can implicitly store names in this structure. Now, it's way too pictorially difficult to depict lots and lots of names in this form. So just imagine in your mind's eye that there's dozens, hundreds, thousands of names now in this data structure with just more arrows and more arrays. How do you actually look someone up in this data structure? Well, if you want to ask a question like, is Toad in this data structure? Or is Toadette in this data structure? Or anyone else? You can simply start at the root node, as we would do for any tree, and you hash on the first letter of Toad's name, which gives you this location, and you check, is it null? If not, T is implicitly there, so you follow that pointer here. And then you hash the second letter of Toad's name, an O, and check this pointer, and you follow that arrow. Then you check the third, you hash on the third letter of Toad's name, A, and you follow that arrow. Then the fourth letter of Toad's name, D, and you see, there's a Boolean here, represented in green, that means Toad is in this data structure. And notice what's subtle here. It doesn't matter if there's 3 names in this trie or 3 million names in this trie. How many steps did it take me to confirm or deny that Toad is in this trie? 1, 2, 3, 4, which is arguably constant. Even though the names can vary, at some point, there's no Nintendo name longer than what, like 10 characters, 20 characters, maybe 30. I mean, there's some reasonable bound that is finite where there's never going to be a name longer than that because Nintendo's never going to come up with a crazy long name for a game. And so you effectively have constant time for looking up T-O-A-D, Toadette, Tom, Mario, Luigi, Peach, any of the other names we've looked at. So this is to say a trie allows you to ask questions like, is Toad in this data set? Or equivalently, what is Toad's phone number in this data set? Because if you assume now that each of these pointers ultimately is not just a bool saying yes or no, but maybe it's an actual person structure with a name and a number, you can store even data like that. Your key value pairs where your names are your keys and your phone numbers are your values. To make this more clear, then here is a data structure how we might represent in C each of these nodes. It's not quite technically just an array. It's an array of size 26. We'll call it children because it represents the children of that node of type struct node star. And then here, for instance, for simplicity, is that person's number if we reintroduce numbers and want to store in this data structure someone's phone number as well. So using that data structure and that kind of code, you can implement a trie using something as simple as this. Initially, your trie is just a pointer to a node, one such struct. We can, of course, initialize it to null to make clear that there's no names in here. But each time we allocate a node, we can then add another node, hashing on the first, the second, the third, the fourth, the last character in the person's name, allocating a node as needed, flipping that Boolean to true or false, or adding their phone number as a char star to indicate that we have then found them. And so of all of the data structures we've looked at today, big O of 1 is actually achieved with tries. And yet, curiously, for problem set 5, you're not going to implement tries. You're going to implement hash tables, that sort of Swiss Army knife of data structures that like every programmer everywhere knows about. Why? Like, why not use tries very often in practice, perhaps? You certainly can, but what's the trade-off, perhaps? Yeah? It's a huge amount of memory. Things have escalated since the start of class. We started with 1 int, then we added an int and a pointer, an int and 2 pointers. Now I'm proposing 26 pointers plus a Boolean or a data structure called person. I mean, it's escalating significantly. And the biggest catch with a trie, as you might have imagined with Toad and Toadette and Tom on the screen, there's a huge amount of wasted memory, just as we saw with a hash function potentially. But that can be reined in, as you'll explore in the problem set with a trie. Most of the pointers in those arrays are just null and unused. And it just tends to result in you're using way more memory to solve the problem correctly, but in a way that tends to slow the computer down and just waste more memory than is useful. That said, just as we started today, there are stacks in the real world. There's queues in the real world. There are even hash tables in the real world, which you'll indeed implement in code for problem set 5. Has anyone here ever had a salad from a restaurant called Sweet Green in Harvard Square? Also elsewhere in the US, like No, one, two, like two of us, three of us. OK, so not hard to imagine going to such a store, getting in a queue, and staring at a shelf like this, because what Sweetgreen and similar restaurants do when you order for pickup is they hash your salad into a shelf like this. And so literally in Sweetgreen, might you see some wooden shelves like this. This is the A through E bucket, the F through J bucket, the K through N bucket, and the O through Z bucket, whereby if your name, like Malan, happens to be in one of those ranges, they will hash my salad and put it here. But of course, even in the real world, there are some constraints. And what can go wrong with this here hash table system? Someone who's been there, maybe. What can go wrong? Imagine like the extreme. Lots of values here. Yeah. So there's no more space, right? So, and this has happened to me in the past, especially since Sweetgreen, before adopting this system. They used to put the A's here, the B's here, the C's here, the D's here, and so forth. And then someone at some point realized that they were very frequently overflowing the A's to the B's and the B's to the C's. No one was using Q or Z with any frequency. And so they were sort of wasting space and running out of space. So at some point, they decided to like literally remove most of the letters of the alphabet, make the buckets bigger and fewer. So now it's very unlikely that you're going to have so many K's through N's that you overflow the shelf. But this is, in the real world, a data structure like we've seen today. And so therefore, among the goals, even as arcane as things seem to be getting with all the pointer notation and dereferencing this and that, really all we're doing in code is implementing real world solutions that other people have already come up with and translating them to a new domain. And the very last thing you'll do in C this week is indeed implement your very own spell checker, whereby we'll give you a very large file of 100,000 plus English words. You'll have to come up with a clever and efficient way to load it up into memory, and we'll give you tools that will actually measure how fast or how slow your code is, how much memory or how little memory your code is, so as to actually compare it against not just your own, but perhaps others as well. So with that said, we'll end a bit early today. We'll see you next time.